Good morning, everyone. In our last two classes, we have talked about the failure of the materials, and I hope you guys will have a good understanding of these failure mechanisms. And from today, I'm going to talk about phase diagram. The phase diagram, this is my favorite part I want to teach you because it says a lot of good things about this is the phase. I think, in my opinion, this is the core, one of the cores of material science. And so here are today's objectives, and we are going to learn the fundamental concepts about phase diagrams, and then we learn this unary phase diagram, and then we learn the binary phase diagram. And based on the name, you can see unary means we only have one the same material. The binary means that we have two different elements, two different materials. And we are going to talk about this in detail. And first, we talk about components and systems. And there are two different concepts. And components and systems. Components, pure metals, we call pure metals, and or the compounds of which alloy is composed. For example, the components are copper and zinc in a copper-zinc brass. This is, these components. And the components, we have this solute and solvent. Um, the systems are referred to as the specific body of material and consideration. And this is a system of, for example, a lead or molten steel, and or it may relate to the series of possible alloys consisting of the same components but without regard to alloy composition. And so here is iron carbon systems. Also, by the way, iron carbon system and is one of the most important topic in the material science. We are going to use on several class sessions to talk about iron carbon steels systems, because iron carbon, so we call the steel. The steels are the most important. This is the materials we have been using in industries, and even though currently there are a lot of other emerging materials, but the newly emerging materials, and they are very, very expensive, and steels are still commonly used materials in industry. Then we talk about the physics. A physics means a homogeneous portion of a system that has uniform physical and chemical characteristics. For example, for this is alpha and beta, and so this is alpha and beta titanium alloy. Okay, alpha, they have titanium alpha, titanium beta, and they have this titanium alpha and titanium beta, and they are different. They are different, so they are called two different phases. When two phases are present in a system, when the two phases, it is not necessary that there be a difference um, in both physical and chemical properties. A disparity in one or other set of properties is enough, is sufficient. For example, water and ice. Water and ice, chemically, and they are the same, but mechanically, this physically, water is a liquid, ice is a solid, and as a result, water and ice, they are treated as two different phases for H2O. One more time, okay? So water and ice, chemically they are the same, but they have one different physical property, and because water is a liquid, ice is a solid, and in this sense, water and ice, they are two different phases. Let me repeat. Generally speaking, as long as there is at least one different either mechanical property, physical property, or chemical property are different among these phases, even though other in other aspects these materials they are the same, but these materials are still called different phases. Do you understand? One more time. If there is at least one different property, and this property can be physical property or chemical property, then these two materials, even though they are the same in all other aspects, so these two materials are still called two different phases. I want you guys to know that. Okay, so when a substance can exist in two or more polymorphic form, for example, having both FCC and BCC structures, each of these structures is a separate phase. So BCC and FCC, this is chemically they are different. And as I said, polymorphic forms. Okay, for example, the iron. We have alpha iron, we have beta iron, we have gamma iron, and they are different. The same as I said for this water and ice. Questions so far? No question? Let me give you a micrograph. This micrograph is aluminum copper alloy. This is beta is a lighter the phase. You can see beta is a lighter phase. The darker phase is a darker phase. And so, by the way, this is a micrograph. Looks like a ground after the heavy rain. Right? After the heavy rain, we have some puddles here. So just like the water, this is light phase. Here is a beta is a lighter phase, and darker is the alpha phase, and they are different. They have two different phases. Questions so far? No question? And then we move on to the next slide. Then we talk about solubility limit and solution. Solution the solution. Okay, solution can be solid, can be liquid or gas solutions, and a single phase. This is called a solution, single phase. Mixture more than one phase. Mixture more than one phase. And solid limit, maximum concentration for which only a single phase solution exists. So this is called solubility limit. And for this diagram, you can see, so this is abscissor is a composition of this carbon weight percentage. This weight percentage. So here is a this is called composition. Okay, for this one, we use the sugar. And sugar, the solid is the sugar. Solvent is the water, and the solution is the sugar water. And so here is the temperature. And so it is liquid, and so this is liquid plus, and this is solid sugar, liquid plus solid sugar. So as the temperature goes, right? As the temperature goes, this the temperature goes. So this composition of C percentage of the sugar and is increasing. So based on our experience, we know that hot water usually can dissolve more sugar than the same amount of water, but at the lower temperature. Okay, so the temperature makes sense here. So question, what is the soluble limit for sugar in water at 20 degree? And for this temperature, this is 20 degree, and we can just draw a line here, 20 degree, and then, so this is a horizontal line will intersect. This is a blue curve at this point. Then at this point, we draw a vertical line. So this vertical line intersects, this is x-axis at this point. It is about 63 something. You can see? 65, okay, so this is 65. And so at the 20 degrees C, and if C is less than the concentration of sugar less than 65 weight percent, and we have syrup, and we have a syrup. And at 20 degrees C, if its concentration is greater than 65, and we have a sugar. Okay, we will have sugar and liquid. Does that make sense? Okay. So effect of temperature and composition. Altering T can change the number of phases. Altering T, you can change number of phases. If we change the T here. So path A to B, you can give you this part. Okay, path A to B. So this is the B, 100 degrees C, and for the C equals 70, this is 20 degree, C equals 70. And if we can change the temperature, we can change the phase. You can see at the very beginning here, we have two phases. One is a solid sugar, one phase, and liquid is another phase. These are two phases, right? However, when this path intersects this blue curve at this point, then past this point, and then we will have one single phase, and this is the syrup. So this is you can see from the changes from two phases to one single phase. So this example, I use this very simple, intuitive company C example of water, how the water dissolves in sugar. I'm sorry, how water dissolves sugar to form this solution, and to illustrate the several concepts. And then we are going to talk about the phases. Altering C can change the number of phases also. You can see from here on path B to D, right? Path B to D. Here is one phase, right? And then if I increase the concentration of the sugar, and then I go horizontally and to this point, at this point, and I will have the liquid and solid sugar, because I know at this point, and so the water cannot dissolve all the sugars I just added. As a result, I have two phases. One is liquid, one is the solid sugar. And then we talk about phase equilibrium. So equilibrium is a plural form of equilibrium. So there are several concepts. Free energy, a function of the internal energy of the system, and also the randomness or the disorder of the atoms or molecules. This is a free energy. And second concept, equilibrium. A system is at equilibrium if its free energy is at a minimum under some unspecified combination of temperature, pressure, and composition. So these are three distinct important factors: temperature, composition, or concentration, or this pressure. And then the third concept is phase equilibrium, and refers to equilibrium as it applies to system in which more than one phase may exist. It is reflected by a constancy and with time in the phase characteristics of a system. So metastable state. It is often the case that a state of equilibrium is never completely achieved because the rate of approach to equilibrium is extremely slow, and such a system is said to be in non-equilibrium or metastable state. A metastable state or microstructure may persist indefinitely, experiencing only extremely slight and almost imperceptible changes as time progresses. And I want you guys to know this is a commonly see concepts, understand what they are talking about. Any questions regarding this slide? Free energy, equilibrium, phase equilibrium, and metastable state. And then we talk about one component unary phase diagram. This what because one component, okay, only one component. So there is no compositions here because 100% of one component. Then that means we only take care of two other factors, pressure and temperature. So here, look at this temperature. So this is the temperature, and so this is the pressure. You can see, so this is the space is divided into three parts. So first one is a solid. This is solid. Solid is ice, right? And liquid and water And the vapor and the steam, it is three different. These are three different the areas. So this is a pressure temperature phase diagram for water H2 hydrogen oxide. An intersection of the dashed horizontal line at 1 atmosphere. So this is 1 atmosphere. ATM means atmosphere pressure, with the solid liquid phase boundaries, solid liquid phase boundaries, point 2. This is 2 and corresponding to the melting temperature at the temperature at this pressure. Similarly, point 3 and corresponds to the liquid vapor boundary represents the boiling temperature when T equals 100 degrees C. So phase diagram indicate phases as a function of temperature, composition, and pressure. So you need to know that. Okay, so indicate phases as a function of these three commonly C factors: temperature, composition, or concentration, and pressure. For this course, the binary systems, as the name suggests, binary system means have two different components. So independent variables, and they have, this is a temperature, and this is a composition. And P is equals 1 atmosphere pressure is almost always used at atmosphere. So this is 1 atmosphere is the normal pressure that human experience, and means that also the materials experience and when in service, right? So that's the reason. So this is P, we use a constant P here. And for this is phase diagram, I'll give you an example of copper and nickel system. And so here is a composition. Okay, this is a composition. This is with percentage of nickel. From 0 means that this all is copper. For this end is all is nickel. So this is temperature. This is temperature. And we have, and this is the two curves. One is called a solidus curve, and one is called liquidus curve. And below the solidus curve, and it is the material is alpha, is a solid solution. So this is a solid. Above this liquidus curve, and the material is a liquid, is molten material. In between this liquidus curve and the solidus curve, we have the two different phases. One is L, the liquid phase, one is alpha phase, the solid phase. So here is the two phases, liquid and alpha, FCC solid solution, and three different phase fields. One is here, as I said, liquid above this liquidus curve, and this is alpha below the solidus curve, and between this liquidus and solidus curve, we have two distinct phases, alpha L and alpha. Any questions so far? So that means based on this is phase diagram, and given a temperature and given a composition of this is the nickel, and you can get this is the intersection of these two. One is horizontal line, one is a vertical line, and you will get and you will know where this point will be located. Then you know what it is liquid or it is a solid, or it will have both of these two phases. So this is a phase diagram. And any questions so far? No question? Then we move on to the next slide. Next slide is called isomorphous binary phase diagram. So isomorphous is a very, very important concept. What is iso? In English language, iso means something is the same, right? So isomorphous here, it means that complete soluble of one component in another. Alpha phase field extends from 0 to 100% with percent. So this is a phase diagram, copper, nickel. system binary, we have two components, copper and nickel, isomorphous. Isomorphous means that, and this is a composition extends from 0 to 100%. That means these two guys, and they have the same crystal structure and also almost the same atom radii, and this is also very similar electromagnetic value, and so these two guys are called isomorphous. That means you can dissolve 100% of nickel, and so from 0 to 100% of nickel can be dissolved in this copper. And this is solid. This is solid solution. This is substitutional solid solution. Do you still remember this concept, substitutional? Okay, if these two guys are substitutional solution, and that means is called isomorphous. That means that, and we can, for this is Abscissor, we can have 0 to 100%. And then we talk about criteria for solid solution, and I hope you still remember this is the Rossary rules. Okay, so this is a simple system nickel copper solution. So these two guys must have, as I said, okay, in my when we talk about the previous slide, must have the same crystal structure FCC and negativity and also radius are very similar, and both have the same crystal structure and have similar negativities and atomic radii have electronegativities, suggesting high mutual solubility. Okay? So Ni and copper are totally soluble in one another for all proportions from 0 to 100%. Then look at here, phase diagram, determination of phases present. And rule 1, if we know the temperature and C0, then we know which phase or phases are present. For example, point A, a temperature composition, alpha, one phase alpha. Second one, point B, 1250 degrees C with 35% of nickel here, and we have two phases, L plus alpha, liquid plus solid. This is one rule. And second rule, if we know T and C0, then we can determine the composition of each phase. We can denote, or we can calculate composition of the phase. Okay, so here consider C0 and 30% nickel at TA 1320 degrees C. Only liquid is present. At TD 1190 degrees C, only solid. And so this is both of them, they are equal to 35% of nickel. At temperature TB, both alpha and beta present, and we know that. Right? So both beta, alpha and beta, alpha and L present, and we can calculate the composition of phases. And how to do that? And we use, this is a timeline, and draw a horizontal line. This horizontal line intersects this curve and this curve at two different points. Okay, Cl equals C liquidus. Liquid here, C liquidus. It equals 32% of nickel. And C alpha here, draw down, draw vertical line down here, And so this is 43. So these two guys and the total average, this concentration of nickel still equals 35%. But for alpha is higher, lower, 32%. For solid is higher at 43%. Do you have sense? So this line is called tie line, a horizontal line, tie line, that intersects the two different lines in the phase diagram. The rule 3, if we know temperature T and C0, then we can determine the weight fraction of each phase. The weight fraction of each phase. Still the same thing here, point B, and we know that C0 is still 35%. At TA, we only have liquid present, right? So alpha, L, weight percent of L equals 100%. Weight percent of alpha equals 0. TD, only solid alpha, WL equals 0, W alpha equals 100%. For at point B here, right? So both alpha and L present, and how can we calculate the weight percentage? And you should know this equation. So this WL liquid is, you can see, okay, so this is WL and W alpha. They have the same denominator and different numerator. And numerator is a change, okay? The numerator for L is a numerator. The numerator equals the arm length from this point B and to the point to the solidus. And however, for this W alpha, the numerator equals the length of arm of this point B and to the point that this tie line intersects. This is a liquidus curve. And so we have, and be very, very careful when we calculate the weight percentage. And so this is called